I'm Ian. I'm going to talk today about some data pipeline engineering that I do at my work. I'm one of the co-founders of Stadia Maps. We do maps and location APIs. We do a lot of our back-end engineering in Rust. I've been doing Rust professionally since 2018. And I guess I would describe myself as a accidental cartographer and data pipeline engineer. My background is in neither of those, but stumbled into the industry and been there for about 10 years. It's been a lot of fun. Before we get started, my talks have one rule: interjections and questions are totally okay. So if you have any questions, comments, or snide remarks in the middle, then please feel free to jump in. Okay, so we're going to talk about data pipelines today, and I feel like I need to define that term. The definition I came up with is a process that consumes data from one or more sources, applies some transformations, usually for the purpose of standardizing things so that you can work in a common format. Data source can be as simple as like a CSV file on disk, or it can be something significantly more complicated, like a Postgres database or Iceberg catalog with a bunch of Parquet files and some object storage. Most of the industry tends to standardize around Parquet these days because it has a lot of nice properties for large-scale data sets. It compresses really well. You can shard it across different files, and it can be as simple as some of our data sets are just like multi-gigabyte CSV files that we read off a local file system. The transformations can also be as simple as just renaming a column. Most of the time for us, it's a little bit more complicated. For example, you have a data point and you want to enrich it with some location context, like this coordinate is in Mapo-gu, Seoul, South Korea. The typical reason for having these kinds of transformations is to get the data into a richer, standardized format. In our case, we're doing it to offer APIs on top of things. So we take data in from hundreds of sources, put it into a standardized format that we can index, and then offer it like for geocoding, search kinds of things. I came to care about this because we do a lot of this kind of data processing. Most of our data pipelines are taking in multiple terabytes at a time. And we need flexibility to iterate really fast as we evolve the products. And so just like hard coding something is not gonna fit that last goal, which is that we'll talk about today. Speed and efficiency are really great as well. We hear about that a lot in the Rust community. But the reason that I spent a lot of time recently engineering these data pipelines is more for the flexibility side, so we didn't have bespoke code for every single thing we were doing. Most of our data pipelines at a high level have this kind of common shape that I would describe in like 3 steps. Step 1, you define the data sources. You would have like a type, we call this a table, but it can be, that's a term we inherited from the database world. But a table could be like a single CSV file on disk. It could be Parquet files. It could be Iceberg catalog or some weird bespoke protobuff. Can be pretty much anything. Location, you need to know where to get this data. It can be a local file system path for developing, testing, things like that. It could be plain HTTP. It could be an S3 bucket. And then the schema, that's a fun one. You need to know what format this data is. How do you interpret each column? And some formats like CSV, they don't have any kind, like there's no typing, it's just plain text. There's no type to it, it's just plain text. So you need to tell it how to interpret it. Is this supposed to be an integer? Is this supposed to be a floating point number? What do you do with invalid rows? Things like that. And then the good data formats are all explicit. Like Parquet has self-describing metadata inside it. Protobuf is the same, so you can know this field is an integer. Step 1, we have our data sources. Step 2, we have the intermediate transformations. I actually don't know how standardized this is in broader industry, but I personally find it very helpful to have kind of a halfway step in the middle where I get the data into a somewhat more useful format or enrich it or filter it, things like that. This is really common when we want to join multiple files, for example. So you have multiple CSV files that are part of the same general data set, but you want to join them all together. Maybe one has a list of some like category metadata, and then another one is the main rows. A lot of data sets are still distributed this way. So having this intermediate step in our pipeline helps us deal with that. These don't need to be materialized on disk. It's just a mental tool that we have in the process to help us deal with it easier. And then finally, the meat of any data pipeline is defining the transformation that you want to do. Database people call this a projection. You can basically think of it as the schema that results when you have a select statement. So you would do like select name, address, lat long, or something from a table. So the schema or the projection in that case would be you have like 2 strings and 2 numbers or something like that. The key properties that we needed in our pipeline are to capture this kind of standard shape, keep the internals of everything flexible at every stage, and to be fast because we're doing this over lots of data. I hope that's readable, but this is just an example for flavor. Very simplified. It defines 2 tables from Parquet files that are pulled from S3 URLs. That pre-flight DDL is the intermediate stage. So in this case, I'm taking in their categories raw, Parquet, and coming up with a filtered subset of it. And then finally, the query is like the actual transformation, and we're putting things into a standardized format and enriching it that way. This configuration language is called KDL. We just happened to use that because it looked nice and it was an easy way to capture the standard shape, but you could do something similar in YAML or TOML or whatever you like. And you see a lot of SQL on this slide, and so I guess my hot take for the evening is that SQL is actually great. A lot of people don't like SQL. It feels kind of old and it's all text-based. You don't necessarily have all these things that we like in the Rust world, great IDE autocomplete, things like that. But for the internals of each stage, being able to specify everything in SQL is really, really flexible. You can just change the query. You don't have to recompile your code. You just change some configuration file with SQL in it, and you can rename a column. You can combine 2 columns, whatever. SQL has been around for a really long time, and it has a really good set of tools that's built into it. It also limits you in some good ways. SQL isn't a general purpose programming language, and I think that's actually a good thing when designing data pipelines because it forces you to focus on just the transformation, just the shape of things, rather than if you were to write this in like TypeScript or something, which is what we had before. That's kind of redundant. It's basically saying the same thing. It's strictly at the configure layer. That's the core limitation, and that's what drives the pipeline. SQL is also extensible, and that's probably not the first word that pops into your head when you think of SQL, but chances are you've probably already used some extensions to like standard SQL if you've been programming for very long. In my work at Stadium Apps, we do a lot with PostGIS, which is a geospatial extension to Postgres, and it includes a whole bunch of functions for doing things like simplifying geometries, finding the centroid of some polygon, things like that. If you worked in any kind of time series data before, you may have run across timescale DB. That's a Postgres extension. And yeah, there are all kinds of, Postgres itself has all kinds of non-standard SQL extensions that are very, very useful. If you've done data science work, you may have used DuckDB. DuckDB also has extensions to standard SQL, and that's the same basic idea. And we'll come back to that in a little bit, this idea of extensibility, because that's kind of core to our use case. And digression about SQL, how do we make it fast? Kind of the secret sauce for this when you're dealing with data at this scale is to avoid doing things like copying too much or having to do too much format shifting, And so Arrow is one of the technologies that makes that possible. It's not the only one, but I'd say it's the most commonly used one in modern data pipelines. So it's an in-memory common format. It can be used in any programming language. There are like great bindings for C++, for Rust, of course. Python also has a great ecosystem around this. It's oriented around doing things in batches, and that's one of the key performance unlocks, is that by processing multiple rows of data in a batch and kind of shifting the way that you look at things, so instead of looking at rows, you're looking at columns. These are kind of the big unlocks that Arrow brings on the performance side. It's zero copy, which is pretty cool because memory is slower than you think. That's a bad typo. Sorry about that. Memory is slower than you think, and the less copying that you have to do, the better. And it also minimizes a lot of this format shifting. If you've done anything with like FFI, trying to pass things across language boundaries, or with WASM, you'll probably hit this a lot, the serialization overhead. And one of Arrow's cool things is it is built into most modern data query engines, like DuckDB, for example, has an Arrow API that you can use internally, and then you can keep everything in the same shared memory format. So yeah, DuckDB. DuckDB is probably what you should use for your data pipelines, unless you have really, really specific needs, which we'll talk about later. Don't reinvent the wheel unless you have to. It's an embeddable database, just like SQLite. It's written in C++, but has great Rust bindings. And our first iteration actually used DuckDB for basically everything.
So as a noob who doesn't do backend, how is it similar or different from like CockroachDB?
So CockroachDB is designed to be distributed. I think that's the main difference. Cockroach, it's kind of like Postgres in that it runs on a server. It's like its own process that you connect to. And I think Cockroach's main claim to fame is the distribution. Is that right, Zishan?
The distribution, the atomicity.
Yeah, right.
There's it's a different model.
Yeah.
For sure.
So I guess I would say
Duck is much more.
They call it like single node
Analytics. SQLite.
It's like an analytic version of SQLite, and I guess I should define that because I hear this term all the time in analytic database. Or you also see like OLAP, OLAP, online analytics processing versus OLTP. The key difference that you should think of is that OLTP, or like Postgres, Cockroach, things like that, they're mostly designed for working on rows individually, whereas analytic queries are designed to, you may not always say aggregate, come up with an average or something. That's the main use case for them, but the OLAP databases are also more broadly applicable to things like data pipelines, where you want to touch every single row and you need to be able to efficiently go and scan every single column, and I just want to do this as fast as possible.
Columnar.
Yes, columnar it is.
So if you've done Cassandra, which is more like a distributed database, it's columnar, but I guess Meta got famous for its use of that. But DuckDB is the SQLite
flavored version of that,
columnar database for doing, I want to do an aggregate, I want to do an average, I want to calculate something.
It does basically everything that it can in memory.
Which is also how Cassandra.
Yeah. Oh, okay, interesting. I didn't realize that yet.
Well, how it would do for queries.
Yeah. And embedded just means that it's like a library that you have in the same process as your application. So like SQLite. Does that answer the question? Yeah, cool. Okay, so DuckDB. If you go and look up a DuckDB tutorial, you will get something that doesn't look exactly like this. They have a regular query API, and then they have an Arrow API. The Arrow API is the one that you need to use if you're building a data pipeline, but it's not the default for a couple of reasons. The one is that it's harder to use. There's this this schema argument that you have to pass in, and I think I'll talk about that in a second. And most of the time, honestly, you don't need it. If you're, like DuckDB uses an efficient representation internally, if you're just trying to get the average over some large data set, you're only going to get like one row back, and that's fine. So it basically depends on how many rows you're going to get back. If you're going to expect to get back hundreds of thousands of rows, then you probably want the Arrow API. Otherwise, you can just use the regular one. So that schema thing, I don't know why. They have two APIs. They have a query arrow API and and the stream arrow API. The stream one is the one that you want to use if you're going to go over hundreds of thousands of rows. If you use just regular query arrow, then it will it will use RAM proportional to your result set size. I don't know why the DuckDB API is this way. I opened an issue up about it, but when you go and call stream arrow, you need the schema, and I should be able to introspect it, but it doesn't. So I don't know why this is the case, but I have a blog post about this if you want the code later. But yeah, I had to write this helper function to go and do a limit 0 version of the query just to get the schema, and then from there I can do whatever I want. Yeah, whatever. Arrow is also not as ergonomic to work with. So if you just use the raw APIs, you'll have these things called record batches, and then in there you'll be able to get the schema object, look at what the columns are, and so on from there. But in Rust we like to have a nice data type for it. So of course someone built a Serday created on top of this Serday arrow, so you can define your record type just as you would normally derive deserialize, and then the query arrow or the batch or the stream arrow APIs will work with this with the Serday arrow from record batch helper. So this is very efficient, by the way. It might look like if you look and try and pick this apart that this is not very efficient, but it actually is. It does all the right things under the hood. So yeah, be careful with query arrow. Like I said, the memory consumption goes up with your result set. So DuckDB is great, and like I said, it's probably what you should use unless you have really specific needs. But its plugin ecosystem is all C++, and that's a problem if you want to extend it. It has an excellent plugin ecosystem. It has like spatial plugins, all that. But you need to write your plugins in C++. They have a C API that's kind of newer and a bit experimental, I think. And then they have an even more experimental Rust bindings for building your own extensions, but that didn't even exist at the time when I was doing this evaluation. So Apache DataFusion it's similar to DuckDB, but it's different. I used to joke that the Apache Foundation is where old Java projects went to die, but times have definitely changed, and there are a lot of truly excellent projects that are coming out of there these days, particularly in the database space. So what's DataFusion? It's a vectorized query engine written in Rust, and that's a mouthful. So vectorized is just a fancy way of saying we process things in batches. Specifically, they process things in batches of columns, and like we talked about a couple of times already, that's where a lot of this performance unlock comes from. This is a pretty popular and not even new trend in databases, so it's a very well-trodden path, and that's what they've built here.
Yeah, you can go to Datalog.
Yeah.
I need to try to make Datalog performant, which it wasn't, but with hardware.
You could write a DSL that converts it into the internal data frame formats, and anyways. Vectorization. It's a really interesting deep topic. I can highly recommend the papers that are published from the database groups at the Technical University of Munich, TUM, as well as the CMU database group. They have a lot of really great papers that they put out, and videos on YouTube. Like they have a periodic seminar series going on right now. Really good stuff. Next complicated bit in there, query engine. What does that mean? So a query engine isn't a database on its own, but it's a core component of every database, and it's responsible for the planning and the execution of the query. It is not a data store though, like it doesn't have a table format. It needs adapters in order to talk to those. So DataFusion has like table adapters for reading a Parquet file, but DataFusion doesn't have its own like native table format. And that's one thing that makes it kind of different from DuckDB, which does. So you just get the part that you just get the part that you need in the case of building a data query pipeline. You just have the query engine. So yeah, it's like DuckDB without that. So why would you use this instead of DuckDB, besides it being written in Rust, which is not the best reason? The reason that we had was we want to write our own extensions to SQL. If we're going to define the whole pipeline in terms of transformations in SQL, then we're going to need to be able to do some things that SQL can't do, or at least not very elegantly. Like, I don't think you could build a reverse geocoder in SQL in a way that it would require a whole lot of gymnastics. But we can just write this reverse geocode function in Rust, and we get these. The UDF stands for user defined function. And so like this reverse geocode function here in the SQL is something that we define ourselves. Defining your own in DataFusion, it used to be pretty complicated. It's a trait under the hood, so like implement the trait. But it used to be a lot of ceremony in order to get that done. It's actually gotten a lot easier, and I just looked at their recent examples while putting this talk together, and so it's actually not too bad anymore. This example here, it's just a closure that has to be wrapped in an arc, and most of the code is not that ugly anymore. There's still a few things I don't like, but yeah, it's you can. There's still a moderate amount of ceremony, but it's if you're going to go to the trouble of writing a whole UDF, like don't do it for exponentiating two numbers, but for embedding a reverse geocoder, like it's actually not too bad. After you create that, it's just stored in this value pow. Then we call create UDF. We give it a function name, so that way when you write a query and there's something invalid about it, or you want to see how it looks in Planner explain things, then that's the name that gets printed. Everything is strongly typed. You have to give it a signature, so in this case it accepts two 64-bit floats and returns another 64-bit float. I'll skip over the volatility stuff because that's not that important, and then you can register it in your context.
So that's not these like the arguments of the type.
Mm-hmm.
The type of the arguments aren't like checked with the original closure that you showed before.
No, they're not.
Okay.
Yeah. You can write your own assertions and stuff in here. And of course, like there's like expect cast failed, but if assuming these line up, and this is like the kind of like I wish they'd have some like macros or something to make this a little bit harder to write wrong code. Yeah.
Yeah. Is there a way to kind of like deserialize them or?
That's what as float64 array does, is deserializing them.
But I guess like you could go from like the type of the arguments that you put into that
like this
macro, and then you could like use the same type to kind of like parse out the arguments.
I wish that it were a macro, but it's not. This is just a regular function.
Oh.
Yeah. So, yeah, that's what that is. You get the function object back, and then you register it in the context. And like we gave it the name POW here, and then now anytime you go to execute SQL, then you now have POW available, or you have reverse geocode or whatever. It's pretty cool. And then around this, of course, like this is just a very like code-centric version, but then around this you can build your own like configuration format or a REPL or something to explore your data or whatever. Last thing I want to explore in the last 5 minutes we have is the way that they use async Rust. You may have noticed that the code samples are all using async. But not everything inside DataFusion is like, it's not like async IO, which is what we usually think of using async Rust for. Particularly in the UDF side, those can be quite CPU intensive. And this is like a design decision that DataFusion made. They're putting everything, including CPU heavy work, on Tokyo and using that for their scheduling. They have some interesting, like Andrew Lamb, one of the maintainers, has some talks you can find online, and he calls this out as one of their design choices. It's kind of split in the community personally. Like I've tried building things this way as well, and most of the time the performance ends up coming out just fine. And this is not at all the bottleneck in any of our systems. So yeah, I think it's an underexplored area in Rust, whether you, like how you schedule these CPU heavy workloads, and their finding was that Tokyo was good enough for them. So yeah, recap, we replaced a whole bunch of bespoke code, like Python and JavaScript, with SQL-based pipelines. We're mostly using DataFusion simply because it's more flexible and we can write these UDFs. If you don't need that, then you should just use DuckDB, great embeddings in every language. Yeah. Maintainers of DataFusion are also super cool, by the way, so big shout out to them. They've had, I've had a couple interactions with them on GitHub, opening issues, submitting minor patches, and they've been super professional to work with. So yeah, very well maintained project, can highly recommend them. Standing on the shoulders of giants here. Any questions?
Is DataFusion embeddable?
Yes. That's, yeah, it's a library. They also have a, like, you can go brew install DataFusion CLI and you get like a little minimal REPL, but yeah, its main use case is a library that you embed.
Can I ask the average data size you normally play with? Is it
Terabytes-ish?
terabytes?
Yeah.
But do you have memory for that?
Oh, we don't need to put everything in memory at once.
Okay.
Yeah,
Okay.
yeah. It's a pipeline. So the output is some other format, like map tiles or Elasticsearch index, things like that.
Then what is your batch memory size? Just for approximately.
Oh, good question. I never really thought about that. This doesn't use that much memory.
Okay.
I think there are some where it might use up to like 16 gigs or something for some intermediate stuff, but it's mostly like caches, this coarse reverse geocoding, things like that. That's where most of the memory goes. That's in this process. The majority of the memory usage, though, in aggregate is the other database that we're indexing things with.
And are you happy with the speed?
Yes, this is not at all the bottleneck. Yeah,
Okay.
yeah. This is ridiculously fast. If I were to just have a null output, not having Elasticsearch or some other process on the other end that's converting to some other format, then it can process hundreds of thousands of records per second on a MacBook. It's very, very fast. Yeah. Cool. Well, yeah, time's up. If you want to find me, that's how you find me. Thanks, guys.